Hi, in today's video we are going to discuss about collaborative documentation tools. So what are collaborative documentation tools? As you can see on the screen, Google Docs, Microsoft Office 365, Confluence and all such tools comes under collaborative documentation tools where multiple users from multiple locations and multiple devices can work on the same document. So this is collaborative documentation tools. Now what if we are asked to design a system on collaborative documentation tools? There could be many requirements like sharing and permission, document formatting or save as or auto save, and many such requirements could be there. But as a scope of this video, we will be discussing two requirements, that is multi-user collaboration and document versioning. So multi-user collaboration is obviously something that multiple users can work on with concurrent editing and real-time updates. And document versioning is let's say with your each save there are multiple versions created of a document. So let's say you want to revisit your old changes, then you can revisit through the version history from document versioning. So we'll be seeing it in detail, its system, how to design their system. So let us first start with multi-user collaboration. So in multi-user collaboration, as you can see on the screen as well, we have three approaches to achieve multi-user collaboration. The first one is locking, second one is differential synchronization, and third one is operational transformation. Now Google Docs use this operational transformation. We'll come to it at the last. Let's first start with locking approach. So what happens in locking? So it's very simple. Let's say there are multiple users. As you can see in this diagram, we have as of now two users sharing a single document. There can be multiple users. So if this user, let's say Adam and John, these are two users having access to this particular document. So when Adam is editing this document, a lock is applied due to which other users, that is John, can't edit the same document. So John is unable to edit the document until Adam stops editing the document. So John is locked. Now once Adam stops editing the document, John can now edit the document. So there won't be any errors or there won't be any conflicts at the same index or same line or same part of the document when changes are made. But this is not real time and this is not concurrent. Like applying locks won't be an efficient solution or won't be a good approach, because let's say if you have 10 users working on the same document, if one user is editing, all the other 9 users are blocked at that particular point of time. So that is not a good approach to move forward. So let us talk about the second approach, that is differential synchronization. So what happens in differential synchronization strategy? Let me show you the diagram. Yeah, so here is just a second, here is differential synchronization diagram. So in differential synchronization, what happens is it is something similar to git diff, where differences are compared from the newer version of the document and the older version of the document. The differences are compared. It is similar to git diff. So a single document has three versions in differential synchronization. One is local, the other one is remote, and the third one is shadow. So the local document is on client side. Local document is nothing but a document on which the user is currently working on, that is a local document. The remote document which is on the server is nothing but the latest saved changes, the content with latest saved changes are placed in the remote version, and that remote version is in server. And shadow version is just a copy of this remote version but on client side. Now what is the need of this shadow on client side? So to compare the differences are compared from this local and this shadow version. Let's say here we have a function called diff which compares the local version and the shadow version, and it brings out what are the new changes. Like you can see here, my name is the content which was earlier saved and is saved in the server. Now there's a latest change, that is my name is Hill. Hill is edited here which is a new word. So this comes under the difference, and only the word goes to the server. The difference goes to the server in spite of sending the whole document. Only the word goes to the server. I mean, the difference go to the server. Now this difference is synced to the remote as well as shadow, and the versions are matched. So this is how differential synchronization work. Let us now look towards its advantages and disadvantages. So considering advantages first, it is very simple to implement because we are only comparing the differences and sending it to the server. And because we are doing this, we can see efficiency in the bandwidth usage as well, which is our second advantage. And the third advantage is lower CPU or memory overhead on server. So we are already computing the difference from the client side. So, and that difference we are sending to the server. So the server won't have additional computations or additional transformations to do, or much more transformations or much more complex operations to perform. So it won't use that much memory and CPU. So there would be lower CPU or memory overhead on server. And coming to the disadvantages, so what are the disadvantages? It is less precise conflict resolution because let's say multiple users, as we are talking it for multi-user collaboration. When multiple users work on a single document, the conflict resolution chances are very less because if a person is editing the same part of the document and the other person, the other user, is also editing the same part of the document, whoever does it last would be remaining in the document. So the last one would win because the first one would do and it will update the document, and the second one, the last one, which does, would be overwritten by the one done previously. So the conflict resolution is less precise. And the second one is inconsistent network can lead to desynchronization. So these are the disadvantages for differential synchronization. So coming forward to the third strategy, that is operational transformation. Operational transformation strategy is used in Google Docs. So what operational transformation does is, let me explain it through a diagram. So yeah, as you can see here in the diagram, there are two users, user 1 and user 2 here, and the existing document contains the content ABC. So this is the current state of the document, that is ABC, right? It would be visible to both the users, definitely, obviously. So whenever at the same time, both the users are performing some operations. So in operational transformation, let me tell you this first, that there would be two operations. One is insert and the other one is delete. So these two operations would be performed after each and every character insertion or deletion, and that would affect the transformation. How? Let me show you. So let's say this user is inserting X at the start of it is inserting X at the start of this word, that means at the 0th position, and this user, that is the second user, is deleting C from ABC. So according to him, the word should be X ABC because he is adding X at the front, and according to him, the word should be AB because he is removing C, right? So that he is deleting from second index and he is inserting at 0 index X value. Now these value XABC would be forwarded for the transformation, that is O1. XABC is stored in O1. So O1 and O2, that is AB, would be would undergo transformation. So after transformation, insertion would be happening at 0th position, that is X. So O1 would be O1 dash would be resulting as XAB, and this O2 will be coming here for the transformation. So transformation of O2 and O1. So this is the scenario for deleting, right? So what will happen here is here the deletion was occurring at index 2. So at index 2, the deletion was occurring, but here if you can see x a b c, x is 0th index, a is 1 index, b is 2 index, and c is 3 index. So now b is index 1, I mean index 2, b is index 2, but his intent was to delete c. He deleted c, right? So why should b be deleted? C should be deleted. So he wanted to delete c. So what will happen is this will compare here in this new value, that means considering the new operation, that is insert operation. So it will compare that is the index which is getting inserted is lesser than the index which is getting deleted. So insertion index is 0, which is lesser than the deletion index, that is 2. So let's increment the deletion index by 1, because one character is being inserted at 0, so which is lesser than 2. So we should increment because so obviously a character is being added, so the string length would increase. So the second index character would be incremented to third index, and the character at third index would be deleted, which would result in XABC. So this is how operational transformation work. So let me even show you a utility which I saw. Yeah, here is the utility. It is, let me refresh it. Yeah, whoever has made this utility is I appreciate that person, because this is very useful for understanding. I can share the link as well in the description of this video. You can go and watch. So there are two users, Alice and Bob here. Let's say Alice is inserting at this position n, and at the same position Bob is inserting a, right? So both have inserted a. Now their changes are not yet delivered to the server, they have just inserted it. Now let's say whoever first, let's say Alice is first, Alice data first reaches to the server, and the action of Bob reaches to the server second. So this was the first. So what was the position? At 11th position a character n was inserted by Alice, and the red one is Bob. So at 12th position, like before transformation is at 11th position, yeah, here you can see. So before transformation at 11th position content A is being inserted. So at 11th position, both are at 11th position, and both have the command insert. So which one to insert first, to insert n or to insert A? Let us see. So if I receive this, so what I got, received acknowledgement of own operation. It was own operation, like it was the operation of Alice, and Alice received itself. And now okay, let's see for Bob as well. So the first input was of Alice, so the first output will also be of Alice in this scenario. Let's say here, so here the transformation occurred. How the transformation occurred, let's see. So this is the before transformation value, that is at position 11 the content is n, and this is after transformation. At position 11 content is n, so that remains same for Alice. Why? Because he inserted first, his request went to the server first. Now similar situation for Bob. So for Bob, he inserted at 11. So this is the before transformation position, that is insert. So the insert position is 11 and the content was A. But after transformation here, which we can see, the position, insert position is 12 and the content is A. So this got transformed based on who sent the request first and who sent the request second. This was the situation where the indexes were same. Now let's see another situation where the indexes are not same, which was similar to what we saw in the diagram. Let's add A here in the starting for Alice, and let Bob remove M. So okay, so let Alice send the request and let Bob send the request. So what will happen here is Alice is getting his own request and Bob is getting Alice's request. So here is the transformation. So initially at position A, content A was added. It was simply an insert, and even after transformation it would remain the same. But in case of Bob, the Bob requested to delete at position 10, but as A was added in the beginning of the sentence, in beginning of the word got an extra length of +1. So here the position is increased to 11 and the length is 1. So this is how operational transformation work. Let us go back to our diagram. Yeah, so this is how operational transformation work, and there is an algorithm inside it. These are only the two use cases which I just shared. There are many use cases and many conditions that are performed under this operational transformation. So let us see the advantages of it. So if we talk about advantages, it has a great consistency. It ensures all users see the same document at any point of time. So that is consistency for us, because transformation occurs for each character. The insertion and deletion command executes for each character that is inserted or deleted. The second one is conflict resolution. This transformation algorithm has a good conflict resolution mechanism. And the third one is it is mature and proven, obviously, because Google Docs is already using it from a long time. What are the disadvantages? The disadvantages is its complexity. Obviously, this algorithm has a huge complexity. Multiple users and large edits, like what we saw was just for 2 users. Imagine that for 10 users working on the same document at the same time. Imagine that for 100 users working on the same document at the same time. So the complexity would obviously be increased. And there could be large edits as well, which needs to be transformed. So those are the complex scenarios. The second one is scaling for large distributed systems can be resource intensive. So this is a disadvantage, but anyhow it is better than locking and differential synchronization. So considering this second disadvantage, let us see what techniques are used to handle that. So polling is not used here. WebSockets are used because of course you want real-time communication, and WebSockets provide real-time bidirectional communication rather than polling, because in polling every time the requests are being sent at a specific time interval and so on, based on what you are using, short polling or long polling. But polling we won't be using here. WebSockets we will be using because it provides bidirectional real-time communication, right? So yeah, that was all about operational transformation, and that was all about multi-user collaboration as well. So let us now talk about document versioning. Okay, so what is document versioning? Let us see here. This is a snip from Google Docs. Let's say I have edited a document on 11:23 a.m. on 26 December. It was saved, the changes were saved. The same document was updated and the changes were saved at 11:53 a.m. on 26 December itself, and the same was saved at 1:11 p.m. On 26 December itself. So which is the current version, right? So this is how we can see the version history, and if I want to go back to this particular change, I can go back, or I want to go back to this particular version, I can go back. So this is version history in Google Docs. So how it is handled, let us see with this example. Let's assume on 26 December. So for simplicity, we'll be considering 2 documents, one for 26 December and one for 27 December. And the one for 27 December would be considered as the current document, right? As a part of this explanation. So if we see about this 26th December document, this is the content in it. Hi everyone, this explanation is made for version. So this is the content in it, right? So imagine this whole document. These are only 4 lines, by the way, but if let's say a document is in KB or in MB, or a document of greater size, there could be a document of greater size. So let's say you make 100 saves in it, 100 versions are created of it. You are editing that document since over a month or over a year. There could be multiple versions of it. So would all these version of such large documents or such small documents even would be saved? Whole documents would be saved in the database for each version? Imagine the amount of memory it would be requiring. So that is not a practical scenario, and that won't be happening anyways. So what is the solution for that? So the solution here is the data is divided into chunks. A Merkle tree approach is being used. So Merkle tree is a data structure. I'll explain you that as well. So let's assume that this content is divided into chunks. Now chunks can be any fixed set of size. For our simplicity, as a part of explanation of this video, what we can consider is each line as a chunk. The chunks could be of each words, or some fixed set of characters, fixed number of characters, or even fixed number of lines. So for our explanation, we'll be considering each line as a chunk. So hi everyone is a chunk, this explanation is a chunk, is made for is a chunk, and version is a chunk. So hi everyone is a chunk. So each chunk, as we would be dividing the document into chunks, each chunks would be then hashed. So let's say hi everyone's hashed comes out as A. This explanation's hash comes out as B. The third line's hash comes out as C, and the fourth line's hash comes out as version. As D. So these are the hashes A, B, C, and D. So these are hashes, right? So how it will be arranged? So it will be arranged in Merkle tree data structure. And how a Merkle tree data structure looks like? It looks like this. So these are the chunks. So A, B, C, D were our chunks. Now A, B are again hashed, and let's say their hash value is AB, and CD are hashed and their hash value is CD. Now this AB and CD are again hashed and their hash value is ABCD. So ABCD we can consider the root node, and the root node would be the hash of the entire document. Now why are we arranging in this particular manner? Why are we not directly finding the hash of the whole document? Let's see. Imagine if we are now making a change in our document. Let's say we are adding a word history in it on 27 December. That document was of 26 December. This is of 27 December. So we are adding a word history here. So adding a word, obviously this chunk, this particular chunk would be again hashed, because this chunk is being edited. These chunks are not edited, so those would remain as it is. So this chunk is edited, so it will be hashed, and the hashed value comes out as E. Earlier it was D. Now the new hash value is assumed it is E. So how it will be arranged? So it will be arranged in this way. So AB, CE, AB, CE, and AB, CE, right? So the root value comes out as AB, CE. So only these hashes are stored in the database, not the whole document. So it saves a lot of memory. After this, now when a user want to retrieve that particular saved change, so what he or she will do is he or she will click on the version, as I showed you in the snip. So he or she will click on the version, and after clicking on the version, what will happen is it will compare. Let's say we had these two Merkle trees, right? ABCD and ABCE. We have these two Merkle trees, so this two hash ABCD and ABCE would be compared. If they are same, the document is same, no changes to be made. If they are not same, then it digs down further. It compares AB, CD and CE. AB are same, so the whole subtree of AB would be ignored for further comparisons. Now CD would be compared, CD and CE would be compared. A difference is observed. So CD and CE would be compared here individually. So C and C are same. So like there could be multiple nodes. Here for example I have taken only 3 levels. There could be multiple levels. So let's if there are any levels under C, then the C subtree would also be ignored. So here E and D have the difference. So the particular chunk has been identified, and that particular chunk which is identified is only updated to our current version when we retrieve the document back from our older versions. So this is how document versioning is handled in our collaborative documentation tools. So yeah, that's it. Hope you enjoyed the video and hope you understand the concept. Thank you.